Uh, oh, hey everyone, welcome to Training Large Language Models with Ray, JAX, and TPUv4s. I'm Sid, she's Joanna, and we both work at Cohere, so let's get started. If I seem a little nervous, it's because my Docker build was failing and I'm reeling back from the trauma. So the overview is I'm just going to talk about what Cohere is, what we do, and then talk about our training framework, which is called FAX, and how FAX interfaces with Ray and our experience using Ray. Maybe a little bit about the future work, and we'll leave some time for questions. This is the last talk of the day, so I apparently have like a 1-minute leeway. So yeah. About us. Cohere is a language AI company. Our goal is to make cutting-edge NLP accessible to every developer in the world. So if you're thinking of an NLP use case, we want Cohere to be the default NLP toolkit for you. We want you to go to the website. We want you to try out our product. And we basically aim to be, the default. And how we do it today is by training extremely large language models on a data set we've curated with care. I know there are a lot of concerns around scraping web data and all of that. So we really put a lot of thought and effort into filtering out data that could be toxic. And we really want our language models to be representative of how we see the world or how we'd like to see the world. So we train these large language models, and we build endpoints around these models that cater to specific use cases in the real world. So that's what we do. And our core offering is a selection of generative and embedding models. And by selection, I mean that they vary in size. And if some of you are not familiar with scaling laws basically say that as you scale up in your model size, your capabilities kind of seem to increase. There are lots of caveats around that, but it seems to, from our experience, it seems to work decently well. So we offer small, medium, large generative and embedding models. And for generative model, we also serve an extra large model. And you can try it out and see if you could use that for like any of your use cases. And we also offer the ability to fine-tune our core models, which are like small, medium, large, on your custom data set. So if out of the box few-shot performance is not good enough for you, you can just kick off a fine-tune, and then we'll serve it for you. And it's very cheap. I think we are the cheapest out there right now. Our product is basically on the right side is a generative snapshot. So all you need to do if you're new to language models is that you just need to show the model a few examples of what you're trying to do. And here it's a movie review sentiment classifier. So you give it a review and say, oh, this review is positive. And you give another one, you say it's neutral, you say another one, say it's negative. And ultimately what you want to do is, as soon as you receive a new review, you want the language model to classify whether it's positive, negative, or neutral. And here, like the darker shade of blue, positive, is the generated token, which means the language model is trying to tell you, based on the context it has seen so far, that the review is positive. And this is like out-of-the-box performance. And it seems to work pretty well based on our internal benchmarks and a few real-world data sets. And on the left side, there are two rows there. The top row is basically a visualization of the embedding space. So you can just upload a bunch of text to our product, and it's going to embed those all of those text data using the model of your choice. And it's going to embed them. It's going to plot them on a 2D space. And you can use that to, however you want, to judge how close sentences are together, or to use that information to drive decisions in products that you want to build off of Cohere. And the bottom left is basically our new endpoint, relatively new. It's called co-classify. And we believe that there aren't a lot of modalities of like text problems in the world. And we want to kind of like build endpoints that are specialized to these modalities. And one of them is classification. You can frame many text problems as like classification problems. And so we thought classify is perfect for that. And you can basically upload a data set and say label them on the OS, which is our product. And it's going to train a classifier for you. It's going to serve it, so you can use it as an API. So that's an overview of the product. And our team's role at Cohere, it's basically we created and maintain Cohere's proprietary training framework, which is called FAX. It's built with Ray, JAX, and TPUv4s. We used to be on TPUv3s. Now we have switched over to TPUv4s. They're pre-general availability, I think, the v4s. So they're exclusive to kind of Cohere for now. But that's what FACS uses to train large language models. And so what is FACS used for internally? First one is our core model offering, which is what I was mentioning earlier, which is generative and embedding models of all sizes. So FACS lies at the core, at the center of Cohere's tech stack, because everything is based around language models. So yeah, FACS powers baseline model pre-training. It also powers customer fine-tuning. So if you go to os.cohere.ai and kick off a fine-tune on your data set, the models are actually trained on TPUs and FACS, and we use JAX. So it's also where internal research experiments happen. So all of Cohere's big focus is also advancing the state of NLP, and not just training large language models. And we also want to be efficient. We also want to be on the forefront of discovering new capabilities and adding new capabilities to language models. And that's how we do it. All of internal research happens at FACS. So a very quick dive into FACS. Joanna will talk much more about how FACS uses Ray and all of that. But a very high-level overview. We have a technical paper out. It's on archive. If the slide deck is shared later, you can actually access the link somewhere. But that's the title. We wrote about it. If you're interested, please read it. Yeah. The core of FACS is JAX's pjit, which is partitioned JIT. And it relies on an SPMD paradigm. For those who have a CS background or worked with computers a lot, it's a single program, multiple data paradigm. So when we have multiple devices, what JAX's pjit enables you to do is it enables you to write code as if you were writing for a data parallel regime, or as if you're writing code for a single device without knowledge of multiple host setup. And you can write this code, you can wrap that function in a pjit, and what it's going to do is perform automatic sharding inference based on your input sharding specification and the output sharding specification. And so pjit does all of that automatically. So that's what's so great about it. The MLEs don't need to worry about how sharding is happening, as long as they just specify how the input needs to be sharded and output needs to be sharded. Everything in between is automatic and powered by JAX's pjit. And JAX's pjit also works with, it requires a few things. So with V4 pods, they're actually cubic topologies. They're chips connected to each other in this 3D torus. And we basically reordered this physical device mesh into a logical mesh of 2 dimensions. The first dimension is a tensor parallel dimension, and the second dimension is a data parallel dimension, which is what you see in the grid next to that. And yeah, we define this user-defined mesh, logical mesh, representing tensor and data parallelism. And we perform all of the pjitted operations within this context of this mesh that we've established. So yeah, that's pjit at a very, I don't know, bird's eye view, I guess. Yeah. And FACS hardware. So a little bit about TPU VMs and multi-host setups. OK. So TPU pods are basically groups of TPU hosts connected to each other. TPU host is basically just, you can think of it as a GCE VM or something. So it's really a VM, and each VM is connected to 4 accelerator chips. 4 accelerator chips forms the fundamental unit of a TPUv4, which is a v4-8. So 8 cores, 4 chips, and here you have 4 hosts. Because each host is connected to 4 chips, you're actually looking at a v4-16 pod slice here. I mean, v4-32, 32 cores, 16 chips. That's a little confusing at times. And a little bit about model parallelism as well, just a background. On the left side, you see pipeline parallelism, which is traditionally how Cohere used to train large language models before TPU pods and even GPU pods came into existence or were really prevalent. So let's say you have 3 devices and 3 layers. So on the left, you see F0, F1, F2, which is basically forward propagation through layer 1 on device 1, layer 2 on device 2, and layer 3 on device 3, and so on. You do the backward pass, and so on. So there's a communication after every device, because you need to communicate activations and gradients wherever applicable when you're going from device to device. And if they're not in high bandwidth interconnect, these communications are expensive. And also you see that when the second device is processing its activations, the first device is idle, it's doing nothing. And this is a classic problem in pipeline parallelism. So you basically want to minimize the overhead of the bubble, and the bubble represents the sum of all the idle times of the devices. So you want to minimize that. There are techniques to minimize that, but it's still not perfect device utilization. On the right side is what you see as SPMD paradigm. All layers exist on all devices. The only difference is that those layers are sharded. But that basically means that after every layer, you have a communication overhead because you need to all gather those activations before you go to the next layer. And this traditionally, if you do not have high bandwidth interconnect, this is a much worse idea compared to pipeline parallelism because you're introducing a communication bottleneck after every layer. But because of TPU pods or even GPU pods, you have these high bandwidth interconnects. In TPUs, they're ICI connects. And this communication is super, super fast, actually. And on the right side, you basically see the step time for train batch size as a function of train batch size. So as you scale up, you see that the slope of the tensor parallelism with JAX and pjit is much lower, which means it's much more scale-friendly as opposed to pipeline parallelism, where your step time just goes up as you increase your token count. Yeah. And some numbers here. On a V4 512, at a batch size of 256, which means 1 example per chip, we can actually achieve a maximum model size of 340 billion parameters and a step time of 6.21 seconds, which is honestly, from where we were 2 years back, it's absolutely insane what these pod topologies can do and how fast they can train large language models. And the same for V4 128, which is 64 chips. You can train 86.6 billion parameter models without going out of memory, and it's a 1.52 second step time. And this relies on a few XLA enhancements and some compilation tricks. But those tricks don't work in a way that puts practicality at like risk or anything. They're just really smart compilation optimizations which enable us to train these models at scale really fast. Yeah. I'll leave it to Joanna to talk about Ray and FACS.
Cool. So let's dive in how we use Ray and FACS. Yeah, so let me go over by the abstraction that we have in FACS and where they reside. So by nature, we need to instantiate a cluster. And we call our abstractions in 2 ways. One is a megazord, the other one is worker. The name is pretty self-explanatory in that megazord coordinates the workers together. So let's talk about megazord first. So megazord is the sort of like the head of the training, as in it handles the data loading, batch splitting, and job coordination across worker. And we have a host VM aside from the TPU VMs that is spawned specifically for this. And this is where the main train loop lies. So if you're familiar with training machine learning model, like this is like where while true train loop happens. And for worker, on the other end, worker resides in the TPU host VMs. So as Sid explained, there are multiple TPU host VMs in a given TPU size. And Ray remote worker handles the processing of the job dispatched from the megazord. And it resides in the individual TPU VMs. And since the TPU chips are interconnected with the faster interconnect, this system of one host VM and the TPU VMs make up a custom cluster for us. And on the initialization, so Leah, let me start by clarifying the word Ray cluster. I'll be saying this a lot, and this is going to be a bit different from the Ray cluster that's in the doc, because we view the system of a host VM, multiple TPU VMs, as a cluster created by Ray, but we do not use the Ray cluster created by Ray because the use case is a bit different that I'll go over later. And this manual cluster is instantiated by the Ray head node, instantiated in the megazord, and TPU VMs connect manually to the head node, the address the head node is created for. And Megazord, during the initialization, Megazord sends the information such as the head node address and runtime environment. So one thing I really want to note about how great Ray is that we send our FACS code-based artifact through Ray runtime, so it gets instantiated through Ray working directory. And this really makes sure that FACS remote code base and the head node code base is in sync all the time. And honestly, I don't think I've ever had trouble with this module. Really cool. And so let me move on to the train steps. So this is like any kind of runtime setup that we have, and a good example that I can give is a train step. So during a train step, Ray head node spins off the batch, it splits the batch in according to the TPU topology, and it feeds into the remote function worker train. Feeding the batch needs to be synchronized. Doesn't have to be like precise, but it kind of needs to be on the same around the same time to make sure that there's a low latency, and this is because of the SPMD paradigm that Sid described earlier. And then each worker feeds the splitted batch into the pjit train function, which spans across globally across the TPU accelerators. And this pjit function does the train step in a distributed fashion, returns a loss, and then the loss gets threaded to the host VM. So this all sounds really crazy, and this sounds really complicated. But with Ray, it is handled by one line, the blue in blue. So it's just like the loss is equal to Ray get worker train remote batch. So it's like Ray really lifts off the heavy lifting that we do on the back end. So let's talk about how we use Ray and what we require from Ray. For us, we need to be able to use a fixed set of identical workers instead of using autoscaler or Ray cluster thereof, and we need to be able to synchronize the workers to run the remote function in a timely manner. And we need to be able to easily implement remote function calls. We only showed you the train call, but we have a lot of different remote calls that we want to run with the TPU, and all of those needs to be implemented through the Ray remote calls. And of course, we would want low latency and stability. We wouldn't want our cluster to die easily, and we want to be able to schedule the train function on the TPU when we call train on the host VM. I already talked about this briefly, but we want to be able to set up the worker environments easily. The one alternative, one way worse alternative for this is setting the environment through SSH and setting the fax directory with this, and Ray runtime environment proved to be so much better. Let me briefly touch about the other use cases of Ray at Cohere. So we use Ray tunes abstractions for our hyperparameter sweeps. We use partial of it, like the distribution functions in Ray tune. And we use the Ray cluster. So this is the Ray cluster that that Ray provides. And we use this for the production fine-tune environment because with the pre-provisioned resources, so already created TPUs, for example. And this really helps us minimize the initialization overhead. Perfect. And so so far, experience with Ray was great. It was really reliable. It has never been the source of our runtime errors. And the ease of implementing the remote calls was very easy. And we sometimes forget a lot of the code base is based on the Ray remote call. And Ray dashboard was very helpful. So when we started building this out, we need to make sure that the nodes are healthy, and then the communication that we see between the head node and worker needed to make sense, and Ray dashboard played a big role in checking all of these. Sorry, what? Okay, awesome. So Sid and I are going to dive into the code examples.
Okay. Cool. Yeah, this is a very simplified example. I'll start by giving a little bit of context around this before I actually talk about the code, because there's honestly not a lot of things going on here. Well, yeah, large language models are large, so everything needs to be kind of distributed and scale friendly. And this could be a big ask in theory, because most of our MLE team, even Joanna and I, don't have a systems background. We have never worked with distributed systems before actually dabbling with FACS and the framework before that. So asking an MLE team with mostly ML research experience and not a lot of systems experience to write distributed programs is a big ask. But we don't want it to be a big ask. We want the barrier to entry to be as low as possible, because to make fast progress, iterations need to be fast. And the framework needs to be really friendly, both for like production environments and research environments. So that's a challenge we've tried to tackle. So here, if an MLE wanted to, this specific example, if an MLE wanted to average checkpoints, and if you're talking about let's say a previous example was a 340 billion parameter model on a V4 512. So if you wanted to average checkpoints, stochastic weight averaging is a thing in the field, and it's been shown to improve performance. So if someone wanted to implement that, something like that, the naive version of it is this code. So let's walk through the code and see what's happening there. And here's how an MLE would do this. They would just import a bunch of utils from facts. One is basically just getting the config with the batch size and the TPU name and all of that. And you initialize ray head node by just calling ray.init. And then you initialize your TPU, which basically creates it and sets up the environment necessary. And it also sets up the ray cluster by taking the head information and the devices that are contained in the multi-host TPU pod slice. And then this is a one-liner function, which is jax.numpy.mean. It takes in a list of tensors, stacks those tensors, takes the average of those tensors along the stacked axis. That's all it's doing. And now the actual distributed part. So all we need to do is our checkpoints are all distributed. We cannot expect 340 billion parameters to be in one NPZ file or a pickle file or something. It's going to break file systems. What we want is basically distribute these checkpoints into multiple shards. And that's what I mean by shard index there. So if we split it 10 ways, there are 34 billion parameters per shard. So let's say there are 10 shards, and shard index can go from 0 to 9. And this average checkpoints from shard function is basically dealing one shard at a time, because they're disjoint sets of parameters. So you can just average each shard and get away with it. And the result is going to be an average of the entire parameter pi tree. And like I said before, everything needs to happen in a mesh context, which is the logical mesh I was referring to when talking about pjit. It takes in a list of devices, that is the logical device array, and we name that as we attach these concepts, tensor parallelism and data parallelism to it. To pjit itself, they mean nothing. They're just strings. But the way we shard things kind of represent tensor and data parallelism there. And the read shards function basically reads the shard from all of these checkpoint paths that we want to average from. So it could just be a bunch of NumPy reads or something. And it's going to give you a list of dictionaries. And the great thing about it is jax.tree multimap works with arbitrary containers. And it's going to automatically map average checkpoint function to all the leaves contained in the shards list of pi trees, which is the shards thing here. And once you get the average shard back, that's what the jax.tree multimap is going to give you. You're just going to write that shard out in whatever way we want. So the result is that we end up with 10 shards of average checkpoints each, and we can load that model and evaluate it and whatever we want to do with it. And the main function is basically just a bunch of remote calls based on how many hosts we have in the TPU pod slice, and array.get of that so that we actually don't exit the program early. And yeah, so it's really that simple to write checkpoint averaging code. Yeah, and one more thing is looking at this code, it's kind of like a really good experience for me, because the conciseness that you get with JAX, Ray, and TPUs and pjit it's hard to overstate the powers of that, because you can really write simple functions that work with Python containers out of the box so well.
Cool. Yeah, so let me just go over a very hugely simplified version of our training workflow. And please keep in mind that this code will not run. This is a very stripped down code. So yeah, so we introduced the remote class worker, and there's a main loop that runs in the host VM that we earlier explained. So really, this is it for us for training the large language model. So let me go over each functions and what they do. So on the worker side, when you instantiate it, you instantiate the mesh that reshapes the JAX devices or TPU devices in the order that you want. And for the simplicity, we are keeping the tensor parallelism as one, and then we are using data parallelism for the rest of them. And given the mesh context, we are going to build the model state and train function. So this model function's constructor will be building pjit function. And when you run train function, it's just as easy as training, writing a train function, which is it just threads down to the train function that you have under the mesh context. And on the main loop, so this is now running in host VM. So let's see what's going on. So when we initialize the TPU, all it does is we make sure the TPU is healthy, and we get the host addresses of the TPU VMs, and we instantiate a ray. We start ray within the Megazord, and we get the ray head info. And we're going to set up the cluster. And this function, all it does is starting ray with the header that's given from the host VM. And then we specify the custom resource called TPU. And we make sure that we require one for all of them. So I really like the way we can set up the custom resources. And this is how we schedule and how we validate our cluster. We need to make sure worker is instantiated once and only once on each host VM of TPU. So this, TPU equals 1 is the key that threads down in the ray cluster, and that's the one that guarantees us to have one worker per TPU. So yeah, after you have that, you instantiate the remote workers, and that's really just one-liner of creating the worker of number of the hosts we have right now. And when you run the train, when the train loop, this is where the satisfaction comes from. All of these heavy lifting or all of the distributed training setup is really lifted off. It's this one-liner, like the one that I introduced earlier. You just feed down the batch, you gather the loss from it, and you just run ray get to make sure they are coordinated. And yeah, this is so I just there's not much to see, and I think that's the beauty of it. Like the using ray and JAX and TPU would have just made everything very simpler for us in terms of designing the cluster and training the distributed and large language models. Yeah, and with that being said, thank you for Ray for hosting us, and yeah, please let me know if you have any questions.
I was just curious. So you mentioned the heavy lifting is done by Ray, but then when you're talking about that, is this architecture of the TPUs, the workers, and everything that you created, is that in a specific way so that the Ray can do this heavy lifting, or you can make any architecture and Ray can handle that? And also, I was curious about the initialized TPU that you talked about. I think both of the questions kind of relate to each other. Is the TPU local, or is it also array TPU? I'm confused about that. Is it in the cloud, or is it Cohere's TPU versus Ray's TPU? I'm not sure about that in the cluster.
TPU is a resource managed by Google Cloud itself, and we work with GCP VMs, but they could work with your MacBook as well, as long as you connect to those TPUs. And TPUs are basically, for all we care, or for all Ray cares, TPUs are basically just a bunch of hosts that are connected to each other. And the actual placement of the model and training and architecture, they're all handled by pjit. And so our usage of Ray is kind of limited to establishing that cluster and orchestrating the placement of code and invoking those remote calls. And once that kicks in, then it's all JAX's pjit and our model constructors and fax utilities.
Right, so the architecture description is still made by, it's not made keeping in mind that you're going to be using Ray in the future. It's just made, and then Ray just adds on top of that.
I think it could pretty much generalize to any SPMD multi-host setup. I'm pretty sure any GPUs, for example, that have multiple host VMs, Ray could definitely play a role in there. It doesn't have to be even accelerators. It could be a CPU, a job distributor across a CPU, which is a Ray's definitely and traditional use case. But yeah, the use of synchronizing the work and synchronizing the train function, for example, really could scale up to any kind of devices with a similar setup.
Hi, can you show the slide about the ray call in the very last slide? Yeah, the very last line. So that's we said we are passing train, which is we are passing one batch to different train function of different workers, right? For all the workers. As far as I understand from this talk, I think, say, 250 TPU chips, each worker will be several chips, right? So how does this batch? How does it work with, like, say one worker corresponds to 4 chips, but I'm passing a single batch to all workers?
Really great eyes. I wanted to add like a simple function that calls split batch, but it was just running too long. We have like a custom. In real life, you'll be zipping like a split batch across a 256 workers, and you'll be passing those part of the batches, especially the one that I showed earlier is like a data parallel training. So you should be splitting the batch into 256 sub batches, and you should be threading them like individually to each worker. But that was a good catch. Okay. Yeah, this is why this code will not run.
Yeah, if it helps, you can imagine JAX.device put calls inside self.train function. Yeah.
And sorry, let me add one more. Like in real life, we use like a JAX's newer newer abstraction called global device array, so that like they handle the splitting of the batch by themselves. So theoretically, it kind of makes sense for us to just thread down the batch, and they should be able to figure this out within the like a pjit function. So, yeah.
We'll take one more question.
Yeah, quick question. So, in your programming model and in your infrastructure, where is the kind of pipelining and where is like the parallelization decision made? Is the MLE him or herself making that decision, or is it handled by Ray? And then also, are you using kind of any scale hosting, or are you kind of working directly with the VMs, and what does that kind of interface look like?
We're working with VMs directly, not any scale hosting. And for the TPUs itself, the parallelization, that's taken care of by pjit. There are really 2 ways of going about it. pjit also is basically an algorithm which is powered by GSPMD. It's a paper by Google. You can read it, I guess. It has automatic sharding inference built in. You can say that my input is sharded this way, and my output is going to be sharded this way. And everything in between, it has the capability of figuring it out, of like sharding propagation. It's got that built in. But if we know, at least for transformer architectures, there are definite ways we know that, like, to minimize the communication overhead, we know how to shard things. So GSPMD also provides this thing called sharding constraints, where it treats them as hard constraints that it needs to obey for the sharding propagation to complete, to finish going through. So we use sharding constraints for like vanilla transformer architectures. And for any custom architectures we have, we just rely on automatic sharding propagation. Sometimes it works, sometimes it doesn't. In the cases when it doesn't work, we look at TensorFlow profiles and figure out where the breakage happens or where the suboptimality is, and we kind of fix that by changing the sharding specification or adding a constraint.
Sorry, I'm just trying to roll back as Sid talks. So just about like a pipeline parallelism specifically though, like we found out internally it's just maybe enough to use tensor parallelism, and maybe it's more optimal just to use the tensor parallelism instead of pipeline, and we've been just defaulting to the tensor parallelism overall. Like this is because we have big TPU pods available, but if we didn't, we would have had to have logic to either choose pipeline or tensor parallelism and build logics around that.